So we have these notes on the squeeze theorem, and it's available online, but you guys have a copy in front of you. So there's a couple of things we want to get out of what we're going to do here in today's lesson. The first is understanding this idea of the squeeze theorem, and different authors call it this. Our book calls it the squeeze theorem, I think, or I'm not even sure if ours does. The notes does. It's also referred to as the sandwich theorem. So the idea behind it is still the same, whether you call it a squeeze theorem or a sandwich theorem. So it's a kind of a sophisticated and important technique in math for proving that limits exist and what that limit is. So that's one thing, is to know how the technique works and to be able to use it. Actually, a couple of years ago, it appeared on an AP test question where you actually had to use the squeeze theorem. And I know when I went to do the grading, there was a lot of outrage there, or righteous indignation from a lot of the graders who were like, squeeze theorem? I never taught the squeeze theorem. I didn't think that was on the syllabus. And it is, so you have to know that. It is a potential question. The second thing is we are going to talk about is this limit that is really an important one. The limit as x goes to 0, sine x over x. So we're gonna apply the squeeze theorem on this limit to determine what it is actually equal to. Okay. So we will, and then it just turns out that it comes up in a lot of kind of interesting kind of limit questions. So once we have actually proved what this limit is, we're going to prove that that limit is actually 1. Then once we have proved that, we're going to use it, and some examples later on in this notes packet here, and there's some different variations and twists on it. So two things, the actual process and the technique, and the second is this is just an important limit to know. Now, down the road, when we learn a little bit more calculus, we're going to learn what's called L'Hopital's rule. And once we know that, this limit would be really easy to find. We don't have to know the squeeze theorem for this particular limit in order to do it. But at this point in time, we do, because we don't know L'Hopital's rule, we don't know calculus yet. So at any rate, we have on this sheet these three pictures of, well, they're kind of the same diagram, but we're going to look at little different triangles on each of those. So on the first one, we have that we are going to look at this triangle right here in the yellow. So we know that this is a circle of radius 1. So we know that this distance here is 1. And this is our angle theta. And so we are going to try to claim that the area of that yellow triangle is equal to 1/2 sine of theta. That's what we're trying to prove. And we want to, so let's start with that and see if we can do that. So if we draw in we know that the area of a triangle is 1/2 base times height. Okay, that much we know. And if we draw in a perpendicular here, then that little orange H, that's the height of that triangle. Are you with me there? So then we can say that in our triangle, the base of that rectangle is the same as the radius of that circle, which we know is 1. So we got that much. Now that H, when you look at that triangle, we have formed a right triangle here with that H, and that's still theta. And because the radius of this triangle, of this circle, is 1, that means this hypotenuse up here is also 1, because that's a radius also. You with me there? I mean, nod to the head. So then using SOHCAHTOA, you know what we know from our right triangle trig, the sine of angle theta is opposite over hypotenuse. And so the sine of theta is going to be that height of the triangle. You with me there? And so our height is going to be sine theta. And so we have the area of this triangle is 1/2 sine theta, which we're going to tuck that 1/2 underneath and call it sine theta over 2. You okay so far? So then we move to the next diagram, and this time, we have the same angle theta, so we're not changing anything there. And the radius of the circle is still 1. And this time, though, instead of finding the area of the triangle, we call it the area of the sector. So we want the area of the sector. So that means we're going to take that little slice of pizza-looking thing that we're trying to find this area right there. And our claim is that we're going to try to say that that area is 1/2 theta. That's our challenge. And we show that that is, in fact, 1/2 theta. Okay? So we know that the area of the whole circle is pi r squared. So that's the area of that whole circle. We know that if we were in degrees, we could say that if this angle is theta, we could say that this is the fraction of the circle that that slice of pizza is going to be theta over 360 times the whole, it's that fraction, theta over 360 times the pi r squared. Does that seem reasonable? But we're in radians, so instead of theta over 360, we're going to say that this fraction of the circle is going to be theta over 2 pi. So this is the fraction. So, for example, you know, if we have something like a 90-degree angle, which is a pi over 2 radian angle, then we know that that would be 1/4 of the circle. Right? 90 over 360 is 1/4. Pi over 2 pi is also going to be 1/4. So that represents the fraction of the circle that this little slice is, times the area of the whole circle, which is pi r squared. But in our case, the radius of the circle is 1, so the r squared is really just 1. So we have theta over 2 pi times, well, we've narrowed that down to being 1. And we can cancel the pi's and get that the area of that sector, it's called a sector when you get that little slice of the whole circle. So that area of the whole sector is 1/2 theta, or we can refer to it as theta over 2. Is that okay? Now we'll come back to it in a minute, and we can see that just from the diagram, the triangle has to be less than or equal, the area of the triangle has to be less than or equal to the area of that sector. And saying we're going to time our blinks here, so that was way, way overdue. Okay? Does that make sense? Okay, I'm going to change colors. Now we're going to now change the triangle here to where we're going to come up here perpendicular. Still that same angle theta. And we're going to find the area of this triangle. And we know the area of the triangle is 1/2 base times height. And the base of this triangle, remember, we still have a circle of radius 1. So this length is going to be 1. You with me? Okay, so that part is 1. Now I'm going to get the height. So again, we're going to use our SOHCAHTOA, but we don't know what the hypotenuse is, so we don't want to use that. So we're going to do a different trig function, and we're going to say that this is opposite, that's adjacent. So the tangent of theta is going to be opposite over adjacent. So tangent of theta is going to be VH. Okay? So the height is going to be tangent theta. That's going to be the area of that purple triangle. And so again, 1/2 theta, or we can call it tangent theta over 2. And that's what we were trying to get for that area. Okay, so far. So what we got so far now is the yellow triangle has an area of sine theta over 2. The sector, that blue slice of pizza looking thing, has an area of theta over 2. And the purple triangle has an area of tangent over 2. You can see from the graph, from the picture, that that we have that the orange has to be less than or equal to the blue, which has to be less than or equal to the purple. So that's our inequality. So I'm going to put that up here. So we can see visually that sine theta over 2 is less than or equal to theta over 2 is less than or equal to tangent of theta over 2. Okay? Remember, back in the back of our mind, we're trying to show that the limit as theta goes to 0 of sine theta over theta is equal to 1. Okay? Now, I should maybe back up for a minute. Let me pause for a minute here, because I haven't really talked about what exactly the squeeze theorem is. And I need to say what that is. But I'm going to clear some space down here, I think. So the idea behind the squeeze theorem is if we have, say, f of x is less than or equal to g of x is less than or equal to h of x. So we have these three functions, and what we really want, what we're interested in is the limit as x approaches c of this middle function g of x. But for whatever reason, it's tough to get at. So this is playing the role of our g of x now. We'd like to know what this limit is, but it's kind of tough to get at. But if we also know that the limit as x approaches c of that f of x, that function that we know is always less than or equal to g of x, if that is equal to some, it has a limit of L, and also the limit as x approaches c of the one that we know is bigger than or equal to g of x, if that also has the same limit, then what the squeeze theorem says is that limit as x approaches c of g of x will get squeezed in between those two. So whatever's happening on the left and right, as we get closer and closer to c, this relationship always holds, but this one's getting closer and closer to L, that's getting closer and closer to L. If that's going to maintain its position of being in between those two, it gets forced to being L as well. Does that make sense? Just the logic of it. So that is the squeeze theorem. And that's what we're going to try to do right now. This is the limit we're trying to get to. Well, we don't have it quite yet, but we're going to work towards it. So this is what we're trying to get. We want this middle piece here, eventually, soon here, to be sine theta over theta. And it's going to be bounded on either side by 2 that we're hoping we can make go to 1. That's our goal. Okay? So let's see what we can do. So first what I'm going to do is I want the theta not in the numerator, but I want it in the denominator. So here's the deal. What I want to do is take the reciprocal of each of those things. But my claim is that, if we have an inequality, when we take the reciprocal of both sides, we know that 2 is smaller than 3, but how does a half compare to 1/3? That's bigger now. So when you take the reciprocal of both sides of an inequality, you have to change the direction. So that's what I'm going to do on both of those inequalities. I'm going to take the reciprocal of everything here, but I'm going to have to switch the direction on the inequalities. It's a long time for one blank. 2 over sine theta is going to be now greater than or equal to 2 over theta, which is going to be greater than or equal to 2 over tangent theta. Okay. Good to go? I just like to have the inequalities going the other way, so I'm going to switch them around. So I'm going to go 2 over tangent theta less than or equal to 2 over theta. You don't have to do this. This is just, I like the organization there better. Now we're going to multiply through everything here by sine theta over 2. So let's go right to left, because we'll deal with this one at the end. So we multiply sine theta over 2 times 2 over sine theta. It's just going to be 1. Okay? Here we can cancel those 2's, and we get what we wanted. We're going to get in the middle exactly what we wanted, the sine theta over theta. Is that okay? Now, the tangent theta here, so now let's do a little aside. We have 2 over tangent theta, which is like saying 2 over sine over cosine theta. So to divide by this is to multiply by the reciprocal. Is that okay? So we can call this, for a moment, 2 cosine theta over sine theta, but then we're going to multiply that sine theta over 2 times that. So the 2's are going to cancel, and so the sine theta is going to cancel. And we're going to be left with just cosine theta. Well, everything we've done here has been to get it to this position. And so all the hard work about arguing about the areas of those triangles and sectors and multiplying by sine theta over 2, all that. So now we can say, look at the limit as theta approaches 0. So when theta goes to 0, what happens to cosine? It approaches cosine of 0, which is what? And this is what we're trying to figure out. And 1, no matter what theta does, 1 is always 1. And so we have squeezed or sandwiched sine theta over theta must be getting closer and closer to 1. And so our conclusion then is that that limit as theta approaches 0 of sine theta over theta is equal to 1. So 2 things we have done. This whole process of trying to pin our limit that we don't know in between 2 limits that we do know that go to the same thing is known as the squeeze theorem or the sandwich theorem. And we now know something that, at least for a while, you're just going to have to remember and know this from memory, because this is going to come up a lot. So this is one of those limits that you just have to know. Now, if you use your calculator, you can graph that easily enough and see it. When you graph that on your calculator, I forget, I think it's going to look something like that, except that it's undefined at 0 because you get 0 over 0, which is a hole in the graph. But the limit is going to be 1. So you can see it on your calculator, but of course the limits I ask you involving this aren't going to be where you can use your calculator. So you're going to have to know it. Okay? Questions on that? All right, so let's turn the page and see some of the various ways that we can use this crazy limit. Now, it doesn't matter what you call theta or not, and let me clarify too. So we can say the limit as x goes to 0 of sine x over x equals 1. So from that we know that also the limit as x goes to 0 of x over sine x is 1. Because it's the reciprocal of 1. So it's the same thing. So it doesn't matter which one's on top, which one's on the bottom. Kind of an amazing thing when you think about it, because what's happening is that this thing, we're saying that these both approach 0 at the same rate. So in a sense, what's happening is if you look at your sine curve, which does something like that, and you look at the line y equals x, which looks like that, what they're saying, what this really is saying is, as you plug in values of x that approach 0 from both sides, these 2 curves, which are very different out here away from 0, really act exactly the same when you get really close to 0. So when you look, right in around here, they're acting the same. They're approaching 0 at the same rate. That's really what that's saying there. It's just kind of interesting to think about. How a curve that's so curvy can behave so much like a straight line in this little narrow region around 0. Okay, so, but that's what that's saying. Now, what you have to be careful of is the limit as x approaches 0. If these two aren't the same thing, then all bets are off. So if I wanted to say sine of 2x over x, now that's not so obvious. That's not going to be 0. And that's part of what we're going to do is play around with that to see what we can do. Okay? This is not 0. So something like this where this that's in the sign and this that's not in the sign are not the same, they are not going to approach 0 at the same rate. So the trick we will do here is we are going to try, now we can't do anything with a 2x that's inside the sign. I can't somehow pull the 2 out of there. But I can introduce a 2 into the denominator. I can't just plug a 2x in there, but I can multiply by 1 in a strange form. So that now I can say, well, let me pull this 2 to join the x down there and leave this 2 outside. See what I did there to maneuver that around? Now that these are the same, as x goes to 0, these, the 2x's in the inside of the sign and the 2x underneath it are approaching 0 at the same rate. Now it's like saying the limit as u goes to 0 of sine u over u, I just called it something else, that limit is going to be 1 times 2. So that limit is going to be 2. Kind of crazy? Okay, well, having said that, let's talk about how in the world are we going to do the limit as x approaches 0 of 1 minus cosine x over x. Well, we try direct substitution. That's our go-to. So we plug in 0. So if we get 1 minus cosine 0 over 0, the cosine of 0 is, that's a hard question too, evidently. Cosine of 0 is 1. And we get, here we are, this is that indeterminate thing again. We've seen this before. Well, the strategies we used before were to factor or rationalize. I don't see anything we can factor, and I don't see anything we can rationalize. So be creative. Think back to your trig days. What might be an option here?
Could you multiply it by cosine plus 1?
Oh, that's brilliant. We could multiply by what we call the conjugate. That's exactly what we want to do. So we are going to multiply top and bottom by the conjugate of 1 minus cosine x. We want to make that be the difference of 2 squares. So now we have a minus b times a plus b. Hopefully this is going to help us. So what do we get in the numerator? One minus cosine squared x. And in the bottom, let's just leave it factored. I got a good feeling. Okay? Now we're thinking back. 1 minus cosine squared x. We've seen this before. What's that equal to? Yes, because we remember our favorite trig identity of all time. Sine squared plus cosine squared is 1. And if we subtract that cosine squared to the other side, we see that our 1 minus cosine squared is indeed sine squared x. So this becomes the limit as x goes to 0 of sine squared x over x times 1 plus cosine x. Okay, you ready for this? Any brilliant insights? Any not brilliant insights? Any insights at all? Brilliant or otherwise? So here's where we're going to tease it apart. Remember, the one thing we know is the limit as x goes to 0 of sine x over x is 1. So we're going to create this limit out of this. So the sine squared, I'm going to think of as being sine times sine. This x times 1 plus cosine x, I'm going to pull those apart. So I'm going to call that sine x over x, so I can create what I want, times the other sine x times the 1 plus cosine x. With me? Are these and these equal? Yes, because top times top is sine squared, bottom times bottom is there. Now, it's true that the limit of a product is the product of the limits. So we can do each of these separately and then multiply the result. Or we can say, this is how you draw a lot of times. You get to draw this kind of funny little sideways arrow. Sine x over x as x goes to 0, we know is equal to 1. Right? That's what we're going to know from memory. Here, I don't know what that is, but we can direct substitute in the 0. Sine of 0 is 0. Cosine of 0 is 1 plus 1 is 0 over 2 is 0. And so we get 1 times 0, that's 0. Limit is 0. Crazy. But kind of fun. You can admit it. Okay, let's do another one. Limit as x goes to 0. And there's an error on there, so I don't want to confuse the issue. And that next line says, here are 2 more examples of limit problems, blah, blah, blah. And it says, limit as x goes to 0, sine x over x is, that's not 0. That's 1. It doesn't change. So change that for me. So limit as x goes to 0 of tangent x over x. Okay, our go-to start is we always try. What is it we always try? Direct substitution. Plug in 0. And so if we plug in 0, we get tangent of 0 over 0. And tangent of 0 is, what is tangent of 0? Tangent of 0, because that's sine over cosine, is going to be sine of 0, which we do know is, over cosine of 0, which we know is, which makes tangent 0 equal to 0. And over 0, oh, here we are, it's indeterminate again. All right, so what do you think? Any brilliant ideas? You've used it all up, Katie?
Yeah.
That was
That's
it?
my weekly.
That was your brilliance for today? Okay, well, how about we think of this as sine over cosine there?
Cosine over sine.
Well, now we, you can't, no, well, no, don't multiply by that, but rather, let's think of how we're going to do the division. So we do this division. Here's our tangent divided by our x. To divide by x is to multiply by the reciprocal. So I'm just going to kind of manipulate this around here. And we're looking for the one thing that we know. Limit as x goes to 0 of sine x over x is 1. So that's going to be sine x over cosine x times the reciprocal is 1 over x. Okay, can you see it? Nod your head yes, but I'm unconvinced. What do we do?
Well, you see the sine x over x, which is
That's what I was hoping you would say. So there's the sine x over x, which we're going to group together. And that's going to leave the cosine x out, 1 over cosine x on an island. But that's okay. Now, as x goes to 0, we know this sine x over x is going to go to 1. And we can direct substitute in 0 into cosine, and that's going to be 1. You get 1 times 1, which is 1. Crazy, isn't it? Okay? So, we did one like this a moment ago. Sine 4x over x, you know what to do? Yes, I think I heard somebody whisper, which is what I was hoping you would say. That's the correct answer. See if you can answer that. I'm going to give you about, 30 seconds, maybe less. Are we thinking similarly here? So the problem is we need this denominator to match the 4x there. Not anything we can do with that 4x. So the 4x is in the sign we have to live with. So we got to manipulate the other one. So we multiply by 1 in the terms of 4. 4, we bring that 4 into the denominator. Now that is going to go to 0, 0 to 1, times the 4 is going to be 4. Okay? Okay, see what you can do. Sine 3x over 5x. Whew! How about that? Time to turn on those creativity flows there. Well, I'd even woke Priya up a little bit. I know that. So Zane. Okay, I'm going to help you with it. This 5 in the denominator, I'm going to pull it out. So I'm just going to pull it out all together. That makes that a sine 3x over x. Now I'm going to make the denominator here, that x, into a 3x. So I'm going to multiply top and bottom by 3. Does that make sense? The real one I don't want, put in the one that I do want. So now we get limited as x goes to 0. We're going to get our sine 3x over 3x, which we want. And we have an extra 3/5 left over. See what I did? So this 1/5 and the extra 3 here, I brought that 3 inside there. And so this is going to go to 1 times 3/5. All right. Stop the video and go to the phone.